Okay, we're going to be talking about particle physics. All right, let me draw the helium atom and I'll tell you why we're going to be doing the helium atom. Okay, so there are 2 protons and 2 neutrons. On the outside, you have 2 electrons. All right, so you've got 2 protons. They have the same charge. So the protons have the same charge. If they have the same charge, what would they be doing? Think about 2 north poles or 2 south poles. You've got 2 negative charges and you bring them close together. Okay, so they should repel, but they do not, they stick together. So there is another force involved. So we call it the strong nuclear force. Okay, so the strong nuclear force is what's keeping the protons and neutrons together. So they keep the protons and neutrons together. They keep the protons and neutrons together. That is the strong nuclear force. We think that the electron is fundamental. We think that is a fundamental. Now, there are 2 types of particles. You've got leptons and you've got hadrons. There are 2 types of particles. The leptons include the electrons. So you've got electrons and a particle called a neutrino. Now the neutrino comes from the sun. So the sun can give off neutrinos and they actually pass through your body. So they pass through your body and they leave unnoticed. You need very sensitive detectors to detect these neutrinos. What is the charge of the electron? Now we're going to talk about the antiparticles now. So what is an antiparticle? Now the antiparticle just is the same particle but different charge. The charge is opposite. So the antiparticle is mass the same. So the mass is the same but opposite charge. So opposite charge. So the antiparticle, it has the same mass but opposite charge. That's the antiparticle. The symbol for electron is E minus. That's the symbol for an electron. If the symbol for electron is E minus, what's the charge of the antiparticle of the electron? E minus is the electron. So the antiparticle is the positive electron, and that is the positron. So the positron is the same mass of the electron, but just the opposite charge. This is the antimatter of electron. Now the symbol for okay, let's talk about the heavier versions of electrons. So these are the normal ones. Now you've got muons, that's a negative charge, and you can have positive muons, that's the antimatter of the muon. And another heavier version of the electron is the tau. So these are heavier versions. Okay, so these are heavier versions of the electron or the positron. Now the neutrino, the symbol for neutrino is nu, Greek. So you can have an electron neutrino, you could have a tau neutrino, or mu neutrino. How do we signify the antiparticle of a neutrino? Now neutrinos are not charged, so it's not charged. However, to signify the antiparticle, we write down a bar on top for this, and a bar on top. So these are antiparticles. These are antiparticles. So anti-neutrino. So these are anti-neutrino. So these are the normal neutrinos. These are the anti-neutrinos. These are the heavier versions of the electrons and the positron. Now, what about hadrons? Now, because these are fundamental, the fundamental particles do not experience the strong nuclear force. So the leptons, no strong nuclear force. No strong nuclear force. So it's no strong nuclear force. No strong nuclear force for the leptons. For the hadrons, it experiences the strong nuclear force. Experiences strong nuclear force. Now, there are two types of hadrons. The two types of hadrons are baryons and mesons. Now, the baryons are made up of 3 quarks. Okay, so what are quarks? Okay, so inside the proton, you have quarks, and this is from experiment. So inside the proton, you've got an up quark, you have another up quark, and you have a down. So we can write down up, up, down. Now, what's the charge of the proton? The charge of a proton is +1. So if these make up the proton, these charges must be a fraction, so fractional charge. Right? So fractional charge. It has a fractional charge. Now, the up has 2/3, 2/3, and -1/3. So the up is, make that equal. So the up is 2/3. You add another 2/3, that makes 4/3, and -1/3 gives you 3/3. 3/3 is 1, so the total makes +1. The proton's made up of up, up, and down quark. What about the neutron? Now the neutron is made up of up, down, and down. So up, down, down. So here you have 2/3, -1/3, -1/3. What do they add up? They add up to 0. Okay, so the total is 0. That's the charge of the neutron. The charge of the proton is +1. What about mesons? Now the meson has 2 quarks. 2 quarks. You've got a quark and an antiquark. So the meson have 2 quarks, a quark and an antiquark. For example, now remember, the symbol for anti is a line on top. So you could have an up, anti down. So what's the charge of that? 2/3. The charge of a down is normally minus, but because it's anti, it becomes plus. So the charge is now +1. So an up and anti-down makes a charge of +1. So mesons are made up of a quark and an anti-quark. They can, for example, this is an example of a meson. You could have anti-up and a down. That would be -1. So that could be -1. Okay, so the mesons are made up of a quark and an antiquark. Okay, let's talk more about the strong nuclear force. If we draw a graph, so here would be, okay, let's do here, this is distance. And on the y-axis, you've got force. So here would be the positive force, here will be negative. So this would be repulsion, and here would be attractive. Now, for the electrostatic force, suppose we're talking inside the nucleus. So let's just have a quick diagram of what we mean. So remember we talked about the helium nucleus. You've got, so this is the nucleus, this is the helium. This is the helium atom. So you've got 2 protons, 2 neutrons and 2 electrons. Now the electrostatic force is repulsive. So this is the distance, the nucleon distance. So when we say nucleon, I mean proton and neutron. So the proton and the neutron distance. Now for the electrostatic force, so this is the electrostatic. So that's for the electrostatic force. Now for the strong nuclear force, is something like that. That is the strong nuclear force. Now here, let's just say, is about 1 femtometer. Here is about here's about 0.5. Yeah, 0.5 femtometer. And then here is around 3. This is not to scale. Okay, so this is not to scale. Okay, so if we look at this graph here, so this is the strong nuclear force. So the strong nuclear force is attractive. So the strong nuclear force is attractive when it is more than 0.5. Is that correct? So it is attractive if X is greater than 0.5 femtometers. However, after 3 femtometers, it can't hold the nucleons together. So it cannot hold nucleons together. After 3 femtometers, it cannot hold the nucleons together. So if X is greater than 0.5 femtometers, it is attractive. And then after 3 femtometers, it can't hold the nucleons together.